Good morning, class. Welcome to the sixth lecture on quantum mechanics. Again, our main reference is Introduction to Quantum Mechanics by David J. Griffiths. And again, I'd like to recommend you to have this book by buying one. You can buy online, I guess. Uh, and in the previous lecture, we knew about the harmonic oscillator, the quantum harmonic oscillator, and we also discussed about the infinite um, uh, square well, the particle in infinite square well, and we knew from those lectures that those systems have energies that are quantized, and they have solutions that are um, I mean easy to they have solutions that are easy to follow, those quantum systems. So in this lecture we'll be dealing with another system, and this system is the free particle system. The free particle system is wherein a particle is not bounded anywhere. So it can fly anywhere. I mean, it can go anywhere it wants, and um, the potential the potential that it has is zero everywhere. So in this case, the free time independent Schrödinger equation, the free particle time independent Schrödinger equation will look like this. There's no potential, the second term. The second term is not there. So if we go back, um, here, there's supposed to be this term, but since zero, the potential is zero everywhere, so this will be just uh, crushed out from the Schrödinger equation. So here, again, so here it's just this one, just the Schrödinger equation. So you can transform this Schrödinger equation. Wait, I have to ask a question. So um, so here you can transform this differential equation into this, where k is this expression. So you can write the energy to be k squared times h bar over 2m in this case. So for this one, for this differential equation, the general solution would be this one. Would be this one. And why are we using exponential instead of sine and cosine? The reason is that the particle is not bounded, and it would be more convenient to use the exponential solutions for this kind of system where there's no constraint on the system. I mean, the potential everywhere is zero, so exponential would be convenient to work. Well, this is this is an analog to to the solution of particle in an infinite square well, um, where the particle just stays in between between the constraint, the potential, the wall resistance of the infinite square well. So for that kind of system, it's more convenient to describe the system in terms of the sine and cosine. But in this case, we can use the exponential because the the particle here is not bounded by any walls. So with well, of course, you can write the time dependent wave function. So you can multiply this by e to the negative I e t over h bar. So here you can get the time dependent wave function. By the way, the e, you can the the energy here, you can just use this expression so that you will have h bar k square over 2m as your energy. So this is just if you put k here, this becomes k square. And so this a kind of wave or wave function, time dependent wave function. So if you look at this term, as you have studied in your wave course, if you can see this term, if you remember this term, if you have two functions, or if you have a function that is a function of this form, x plus minus velocity times time, if you can find this, this is a function of a wave. And if you have a function that is x plus vt, that's a function, or that is a wave function that's going to the left. If you have x minus vt, that's a function that, or that's a wave function that's going to the right. So you have learned that in your previous courses. So this one here, the hk over 2m looks like a velocity. It's it's a velocity here. This one, um, it's the velocity. But this one is um, going to the right, and this one is going to the left. So for the negative one, negative here, it's going to the um, to the right, going here. For the positive one, it's going to the left, or negative positive direction at speed v. So that's it. So this is again the solution to this is again the solution. Um, this one is the solution to this differential equation, and then the time dependent solution would just be this. So now we simplify this solution because we have waves going to the right, going to the left, and that's just determined by the sign of k, the sign of this k here, the propagator, the vector propagator of the wave. Um, the k could be positive or negative, depending on the direction. So if k is greater than 0, k is greater than 0, that's a wave traveling to the right, and if k is less than 0, that's a wave traveling to the left. So we can just write k in terms of this, but we can just um, unify these two terms here. We can unify these two terms um, to be just one term like this, but we just have to note that this one, we just have to note that if we have k that's greater than 0, that would just be wave traveling to the right, and if k is less than 0, that would just be wave traveling to the left. So here k is for this for that one there, or also for this one. Okay, so it's just so we can now get the velocity of the wave. So in here, this is the velocity, h bar k over 2m. This is now the quantum speed of the wave, the quantum speed of the wave. But is this really a quantum speed of the wave? Let's see in the uh, let's see in the let's see in the following slides. Classically, the speed would have been square root of 2 over square root of 2e over m. This is twice the classical velocity is twice the quantum speed here, because you have classical equation would tell you that the energy of the system, or the energy of the particle, will just be 1/2 mv squared. That's the kinetic energy, because it doesn't have potential. It's not constrained by any potential anywhere. So it has purely kinetic energy, which has 1/2 mv squared. So um, your speed of the wave would just be 2 over 2 square root of 2e over m, which is twice the quantum speed. So you get E here. So there's a paradox that the quantum mechanical wave function travels half the speed of the particle it's supposed to represent. But um, should they be traveling in the same speed? So anyway, let's look at more what um, uh, free particle will really how the free particle really behaves. So in this case, the wave function here, if you try to normalize it, so how do you normalize? You get the value of a. But here, if you try to normalize this one, that would give you this integral, an infinite one. Therefore, a is not doesn't have a value. In this case, um, it's not normalizable. So therefore, the separable solutions do not physically represent um, realizable states for the free particle. So in this case, um, a free particle cannot exist in stationary state, or there is no such thing as a free particle with a definite energy. So that's what it means, because it's not normalizable. Because this is how to normalize the wave function, and in this case you get infinity. So but what is done is that, um, of course, the general solution to the time-dependent Schrödinger equation is still a linear combination of separable solution, but it's now in the form of an integral. It's not summation, because we are now dealing with continuous variables. Your your contributions to, because in harmonic oscillator or in infinite square well, you have discrete wave functions for discrete energies, for associated discrete energies. In this case, you are allowing um, the free particle to have continuous energy. The particle has continuous energy. In this case, the contributions would also be continuous. So K can have a continuous value, not discrete. You cannot have n equals 1, 2, 3, 0 for wave, um, for particles, for free particles, I mean. So in this case, um, to to kill this argument, to kill this one, we had to take this one, because the amplitude or the contributions would now be, we'd now be accommodating continuous amplitudes, where, unlike in the harmonic oscillator or in the infinite square well, where the amplitudes had to be discrete, here the amplitudes are continuous. 1/2 pi here is just a constant. We will know why it's there in later on. Um, so if you put uh, if you put this inside, if you put this factor inside here, it will look like this. It will look like this, and that is now the replacing the role of Cn in equation, in this equation. Uh, this is the general, for separable solution. This is the general wave function, time dependent wave function. So you have the Cn here, and the Cn in the free particle is replaced by um, is replaced by uh, is replaced by this one, replaced by this one in this case for the free particle. So what's the difference between free particle, harmonic oscillator, and infinite square well? The infinite square well, um, the infinite square well and the harmonic oscillator, they have discrete energies, quantized and um, discrete, meaning the energy, for example, of the harmonic oscillator is like 1/2 h bar square, 1/2 h bar square omega for the harmonic oscillator, and then the next energy, the first excited state, would be 1 plus 1/2 uh, 1 plus 1/2 times h bar omega, and then the next energy after that is would be 2 plus 1/2 times h bar omega. But for the energies, but for free particle, it's continuous. You have an energy of 1, and then you also, it can also have an energy of 1.0001 or 1.0000009, for example. So you can admit any energy for the free particle. So look at this. If you set t equal to 0, or at the initial time t here, uh, x psi x 0 would be just this one. Um, uh, if you compare it with this is just 0, so it will just look like this. So that's still 1 over 2 pi integral of negative infinity to positive infinity of phi k e to the ikx. This one is just a Fourier series, a Fourier transformation. So you know about Fourier transformation in your mathematical physics, and this is just if you have a problem, if you have a function that looks like this, if you have a function that looks like this, it looks like this one, dk e ikx. Your fk and your phi k would just be this one, the integral, and then 1 over 2 pi. This function, which is that one, you can get fk, you can get this fk, which is this one, by using this formula. This is called the Plancherel's theorem. So this one is um, associated with this one, so that um, your fk can be found by using this integral. So if you know this, you can get fk here by doing this integral. Or if you know this, if you know this integral, or if you know this function, you'll be able to get f of x here. You'll be able to get this, so that you'll have an information about this function. So in this case, is this normalized? Is this a normalized function? So by the way, you can write phi k. So if you know this, which is that this one is just this one. So if you know this, you'll be able to know phi k here. You'll be able to know phi k, which is in this expression. So this one is just, or this one is just equal to this, equal to that one. So now we may I just read this essential idea. A wave packet is a sinusoidal wave function, or a sinusoidal function whose amplitude is modulated by phi. It consists of ripples within an envelope. So let's look at the wave packet. So this is now the wave function, or the geometrical representation of the wave function of a free particle. Look at this. It doesn't have a constant amplitude. You have a continuous amplitude. Here you have a small amplitude, and then you have a large amplitude, and then you get smaller again, large, and then it goes to a smaller amplitude. So you are allowing continuous energy, continuous amplitude. So this is a wave packet. Packet that says it's like um, it's um, it's kind of a lump of energy. It's kind of a lump of energy. Like for example, a photon would have a lump of energy, and if it hits a wall, that energy would be absorbed by the wall, for example. So the energy of that one could be different from each photon that would, or from each wave packet that would um, hit that wall. It's not constant. Maybe the energies are close to each other, but um, they could be really different. So if you look at this envelope or a wave packet, this envelope of waves, they travel in a group velocity. All the waves, the combination of the waves travel with a group velocity. And then each wave has, or each ripple has a phase velocity. Each ripple here could be traveling faster than the other ripples, or the other ripples could be traveling slower than the other ripples, or some ripples could be traveling at the same speed. So those are the phase velocities of the ripples. But as a whole, the wave packet, the wave packet will be um, traveling with a group velocity. So, um, and the most important quantity here that's really associated with the wave packet is the group velocity. It's the group velocity. By the way, the wave packet can be represented by waves. It doesn't have to look like this. Like it could also look like this one. Could also look like that one, or it could also look like mm, this one. Could also look like that. So, or it could also look like this. It could also look like this one. So that's a wave packet. This one is just an exaggeration because we know that it admits continuous amplitude. So that's a geometrical representation of or an illustration of a wave packet. So again, phi k, which is here, would just be this one. So if you know this form, then you'll be able to get this by doing this integral. So now you have um, so now you have a wave that looks like this. This one. Um, Omega is equal to k square over 2m. This is the energy, right? This is the energy. We look at the, or I mean, this is the um, associated. If you get the square here of k is just the associated velocity of the of the wave. So here is the energy. Omega is associated with the energy, but if you get the square, if you get this square here, it's the velocity. So um, we are going to find a formula, or we're going to find the behavior of uh, of omega as a function of k, um, in which we could find the velocity um, of the wave packet that will apply to any wave packet regardless of the dispersion relation. So I think you have encountered this term before. So anyway, let's look at the um, the wave packet. Let's have a wave packet that is narrowly picked about some particular value ko. So let's look at this. So for example, you have a wave packet that looks like this, like that. And it's narrowly picked at k ko, for example. So if it's narrowly picked, write we can write the omega k. Um, look here. Um, we can write the omega, since we're looking for an omega that's a function of k. We can write the omega in terms of the Taylor series or expanded Taylor series, and neglecting the higher terms, the Taylor series would just be equal to this omega k as a function. You can write this function as a series, Taylor series. This is omega sub o. This is the value of omega at k sub o plus the derivative of omega evaluated at k sub o is this one. So we can write this because we have a narrow wave. We can write this. Um, we can write this and put it here. This one, we can replace this omega with this. If we have a if we have a narrowly picked wave packet. So with with this omega written as this, so that we can write our omega here, and then we change variable from k to s equals k minus k sub 0, so that our k here will be k plus s. Your k would be k sub o plus s. So here it's k. So it's k plus s now. Your k here would be ko plus s by changing the variables here. And our omega, in this case, omega is, by the way, omega is associated to the energy. And again, omega should be continuous because we are admitting continuous energies. So your omega would be written as this one. This omega sub o here is the derivative of omega evaluated, derivative of omega with respect to k evaluated at k equals 0 times k minus ko. So this one, your k minus ko is just equal to s, so you have this term now. But if you look at this, if you change this to 0, so this one will be eliminated because t is 0. You will only have this term. And look at this term. This is just equal to um, uh, this is just equal to what? Um, this one is just equal to uh, here. Look, k ko plus s is just equal to k, right? So this is kx. So if you have if you, because we change variable, this is just ko plus s will just be k, and yeah, ko plus s here will also just be k. So we have derived the same expression, and at later times you can write this as with your x here uh, minus omega sub o times t. Of course, this is for the later time, this one, and of course, this one also. So that is for for the later time. You can factor out. You can factor this out. This exponential, this one to here. You can factor this omega ot outside, and this one you can with with the k, with the k minus k sub o, you can factor this out of the integral, because this is just constant. Um, this would not be, t would not be function. I mean, you you're just integrating with respect to s here, so your t can go out also. K sub o is constant. Omega sub o prime, or first derivative of omega sub o evaluated at k equals k sub o, is also just a constant. So you can take everything. You can take these things out of the integral and have this. So looking at this equation, this one just looks like this one here. Only that um, only that there's a difference between x and this one. But in general, the ko plus s is equal. This one are equal, and the pi 1/2 squared of pi is just the same. So you can write the time dependent wave function to be this. You can this one. Uh, because this is like x here, and you have x here, you have x here, you have x here, and you have x here. And in this case, you have x minus omega sub o prime t. So your psi would look like this. So your time dependent wave function is now like that. So anyway, now so your wave function has now a phase factor, or uh, a phase factor here. If you compare this with this one, it has a phase factor. If you compare this one with this one, the difference is this factor here. Look at that. There's nothing, and then you have uh, this factor also as some difference. So um, there is now, as I've said, what is this? This one is, if you go back to this argument here, if you go back to this argument, you have a wave function that is traveling with speed v, either going to the left or going to the right. For a function, for any function that is a function of this form, you have the speed here v. In this case, um, the function is a function of x minus prime, omega prime sub o, and this is the uh, the group velocity of the wave, which could be traveling from left or in this case, this is traveling to the right. It's going to the right. So this one, what is this? This is just the derivative of omega with respect to k. So the group velocity now is this the derivative of omega with respect to k. But of course, the the speed of the ripples will just be omega over k, where omega is a continuous value of k. So what is the derivative of omega with respect to k? So this is our omega. So if you get the derivative of omega with respect to k, that would just be h bar k over m, whereas our omega over k is h bar k over 2m. This is this is twice as great as this one. So now, so as I told you earlier, um, this confirms that um, the wave packet is having a group velocity that is equal to twice the phase velocity. The classical velocity is the same as the group velocity of the wave packet and twice the phase velocity. So this is our lecture for today about the free particle. So a free particle is different from the harmonic oscillator because a free particle, or different from an infinite or a particle and infinite well, because those two, the harmonic and the infinite well particle, have quantized energy, but the wave packet does not does, although it has energy, but energy is continuous. It accepts all amplitude, it accepts all energies. So, and they're just lumped in one packet. And in one packet, it's a combination of energies and amplitudes. And that packet has, of course, an energy, which is the energy of the wave packet is given by this. Um, the energy is given by this. But again, the K is continuous, so your energy is continuous. So that's how we describe the wave packet. So I leave you to read the slides again. Um, so from free party for the free particle, this is a little bit tricky. This discussion on the free particle is a little tricky because in the first the fact that it's not normalizable by separable solution, we have to um, resort to a wave function that has that admits all amplitude by this one here. And this 2 pi, this 1 over square root of 2 pi is actually coming from the Plancherel's theorem. This one. That's why you had to include 1 over 2 pi in this wave function here. So and of course the wave representation of a wave packet looks like this. And it's not just a single wave, but a group of waves traveling in a group velocity, with each wave traveling with a phase velocity. And the speed is just equal to um, the speed of the wave, the group speed is just equal to the classical speed, which is twice the speed of the waves inside the group here. So I hope you understand a little bit. And um, next lecture would be dealing on delta functions. So that would be next week. And after chapter 2, we will be doing an interaction sessions where we will discuss sample problems. And then I hope the three of you could join that interactive session. Um, I think via Google Meet or Zoom. So that would be one of my uh, that could be one of our mode of assessing you in this course. So far we have still chapter 2. In chapter 3, we will start chapter 3 after the interaction sessions that we will do later. So next meeting we will do this direct delta potential. Yes, the group. There's a question here. The group is the group velocity traveling to the right because of the what was the question again? It's lost. The group velocity traveling to the right because of the operational sign negative. In this particular equation, it's supposed to be plus minus, but in this case, we just because we already included our sign. Um, we already included the sign of k to be here. Your k could assume a positive or negative value, so it doesn't matter for as long as you know the sign of k. Uh, the k would be k could be anything. In the wave packet, some waves travels to the right and some waves travels to the left. But the wave packet just goes everywhere in space, and so k could be to the right, could be to the left. Um, well, it doesn't specify which direction, but in this form, the negative sign here would just be coming from our approximation to Taylor series. But k could be the wave could be traveling to the right or to the left. So anyway, we will do these things uh, in we will do these things in our interactive session or in our interaction sessions in the future. So I think it's just up to here because the delta function potential would be too long to discuss, and this will be the next topic. So have a good day. I hope you get some a little bit of something in our lecture. Thank you so much. See you next lecture.